diagonalization forms also remain transient as a magnitude tail, but those are related to other disciplines at GEM, including reconnection, substone, but the interesting thing is that those are also connected to day-side and inner magnitude physics. So that's the point I will make through this presentation. So tail physics is closely related to all sorts of disciplines at GEM. So secondly, we're going to start a new focus group about substone polar cap. So I'd like to talk about the theme of that focus group. And this is a tutorial, but this is also a GEM. So I'd like to spend enough time in talking about science questions rather than just reviewing papers. So number 4, so we have results about day-night coupling for tail reconnection substone triggering. So that's a kind of new result that we are recently showing in meetings. So I'd like to talk about the scope of that research and result. So perhaps many of you know the plasma sheet is full of bursty flows. Perhaps one of the most known papers, Angelopoulos' 1996 paper, where he showed that there are a series of flow bursts in the south panel here. I don't have a pointer, but perhaps you can see in here. I shouldn't step back from the microphone, so I guess I need to be here. So those fast flows are related to a series of dipolarizations, and those are occurring during a time when the A index goes up, meaning that those are closely related to substones. And by using the recent MHD simulations, we can successfully reproduce the transport process like in the movie running on the right. So there are the channels of reduced entropy plasma. So by the way, this is entropy distribution at the equator. So you will see the reduced entropy flow channels propagating from the reconnection region towards the inner bubbles. This works perfect. So there are channels of low entropy fast flow channels coming from the reconnection region to the inner plasma. Those are associated with strong electric field. So that if you run a particle tracing like you often run here, associated with the dipolarization flow, you see a strong particle injection going up to a few hundred keV in this case. So those are the important seed population for radiation belt, the rain current, for precipitation to the ionosphere and also driving the aurora. So a number of modeling and observation has been done about this perspective. Perhaps the best example for illustrating this Earthward propagation is Andre's dipolarization flow, where he showed that the outermost satellite measured the dipolarization flow first, then the inner satellite saw the similar changes. Now, I'll look at the detailed signature of this. So this is a TEMIS E data. So this dipolarization is exactly the same as shown here in red. We saw that this is associated with ion and electron injection as well as Earthward flow burst. He also looked at the aurora data. This is orokilogram, which is the latitude versus time diagram of aurora data. So where he saw that there's a substantial auroral intensification followed by an equatorial streaming. This is called an auroral streamer. And if you look at the two-dimensional form, you see that this is a north-south elongated structure propagating equatorward. And so you can see that this is a structure pretty narrow in longitude. So you need to have the satellite somewhere pretty close to see this kind of signature. I'll come back to this point somewhere later in this presentation. And also, this is signature propagating from high to low echelon. So this is the ionospheric signature for particle injection of bursty bulk flows. So in other words, aurora is very useful for detecting location and evolution of fast flows or injections occurring in the tail. So more about the tail inner monocular coupling thing. So on the left, we see an orokilogram again showing a streamer propagating from high to low latitude. But in this case, the streamer didn't stop at the equatorial boundary of the auroral oval, but connected to the sub-auroral diffuse aurora. Later we confirmed this as proton aurora based on our precipitation data. And at the same time, if you look at superar data, there is substantial flow enhancement at the same location as a diffuse aurora in the sub-auroral region. In this case, we have TEMIS satellites, where TEMIS B was sitting at the diagonally measuring dipolarization and also fast flows. Several minutes later, TEMIS C at geosynchronous orbit showed ion injection as well as EMIC wave enhancement. So But this example is telling us that the transient injection coming from deep in the tail to the nearest plasma sheet is bringing the plasma to geosynchronous further into the inner magnetosphere and changing the wave particle interaction process and giving precipitation and also driving the currents to drive fast flow in the ionosphere. But those examples clearly tells us that there are strong tail inner magnetosphere happening going on. And also those will bring lots of interesting questions. And some of them are summarized here. So perhaps from the inner magnetosphere point of view, the most interesting question in terms of this perspective is whether we can predict particle injections. If we can do this, this will be a huge impact on the wave current, wave particle interaction, radiation belt, and subphysics. More specifically, we want to know when such injections will occur, and where injections will occur, what MLT and what MLT width, because those are normally localized. But lastly, we want to know the strength and penetration of the injection, and those can be easily translated to tail language in such a way that we want to know particle injection, but we need to know the reconnection and substorm in order to understand how the injection gets started and coming to the inner magnetosphere. That by itself is important for tail and overall dynamics. And the timing of injection means that we need to understand what is triggering the tail reconnection and substorm onset. In terms of location, we need to know where reconnection occurs and what size. And lastly, we need to know how a reduced bubble entropy is created in the reconnection region. So you can see that there are lots of common interests between the tail and the inner magnetosphere physics. So we need to see this coupling process to understand the whole picture. So let me talk about three examples. The one is that we do want to understand the timing of substorm. So to do that, we need to see if there's any precursor to substorm. We can find that there will be a response. So here's another diagram showing the substorm onset occurring here as a sudden brightening along a pre-existing arc, followed by a large polar expansion. And this coincided with the dipolarization of geosynchronous, so injections are going on. So interestingly, if you look at this diagram, there is a precursor faint auroral form going on. This is a log scale, so this is a really faint auroral form, but clearly forming somewhere in the middle of the auroral oval, perhaps coming from a higher latitude. It's harder to see the scale, but it is indeed propagating from high to low latitude, meaning that there's also a plasma transport going on. Once this comes close enough to the growth phase arc, then substorm takes place, followed by a large vacuum. So this issue has been one of the most fundamental but also controversial topics in the past 4 years or so in tail physics. But there are lots of examples, including this one, showing some sort of precursors in the auroral data. So the question is if this kind of precursor is causally related to substorm onset, or just happen to be there, or this is happening all the time, or just for some particular event. So we need to understand what kind of precursors we have. And if we are sure about this sort of precursors, that may tell us that we can sort of predict substorm onset by looking at the strain activity. But if we want to connect to injection, the timing issue becomes really a problem. So if we go back to untrace dipolarization event, you may notice that the new intensification is happening way after the first brightening occurred here. So this is the substorm onset initial brightening, but by looking at tennis satellites, there's barely nothing going on at that time. So it took a long time until the aura brightened again, then injection came to satellite location. So the big question is what is going on this time? Perhaps a new reconnection happening here, but something has to set off this reconnection. What is going on here? We'll come back to this one later. And certainly I've been talking about tail in the magnetosphere mostly, but I've come to the point that the dayside transients are also included in this picture. If you look at the auroral kilogram of dayside, so this is the auroral near the cusp region, there are lots of transient brightening going on, followed by polar propagation, or PMS. Those connect to polar cap air group patches. So similarly, in the night side, or oval, we see lots of auroral brightening looking quite similar to this, except that these are propagating equivalent. So those are eight-fold auroral strands, being closely associated with fast flows in the tail. So by looking at different regions of auroral data, we clearly see that the transient in both regions are happening almost all the time. And we know that those are somehow related to recollections. So the question is, if those recollection regions are talking to each other to somehow make this sort of process, or this is just an independent process that happens to show somewhat similar behavior. So that's a kind of broad background why we think we need to continue substone research activity and why we are proposing substone focus group. So those are 4 people met and came to this proposal, and this was selected, and we're going to start this activity from today. But let me go into more specific questions of what we think we should discuss in this focus group, and in broader sense in substone community. One is why we have to continue substone discussion here. So traditionally, as many of you have heard, there are 2 types of oral or precursor sequence of substones. One is called outside-in scenario, where the reconnection takes place first, gradient flows into the plasma sheet, then onset takes place. Another one is called inside-out, where the onset occurs spontaneously in the nearest plasma sheet, then the sequence properly tail will trigger the reconnection here. And previously, there have been lots of attempts to solve this problem, but it has been really difficult because we only have a few satellites or some global imaging to see this temperature. But we didn't have much observation in the wide scale, but maintaining the high resolution capability. But that drastically changed as the arrival of tennis. Well, for example, in the science paper, we had a nice conjunction between satellites and ground-based measurements for precisely identifying the timing of tail and ground signatures. Also, in Tony Ruiz's paper showing the flow propagation in multiprobes, so that we can identify timing in different regions of the tail. And those kind of things were discussed in the previous substone focus group that ended in 2013. And also, another important point is that we got a network of ground-based observations where we see the ground-based all-star camera that gave us a continental scale of aurora, but maintaining high resolution capability for detecting the auroral stream as propagating from high to low stream. These kind of things were only seen when those are bright enough or wide enough if you look at previous globally. Also, we have ground magnetometers, radars, and GPS, and so on to provide the wider scale coverage of the sequence. And those are nicely coordinated with TEMS and other satellites. So let me show you 3 main issues that were discussed in the previous substone focus group. The first one is Larry Kepko's idea, which is kind of traditional outside-in. So please focus on this red movie where the substone onset will occur along this pre-existing arc right here. But there is an interesting precursor auroral bond going on that forms right here and appears to collide with the pre-existing arc. So that's again the signature of fast plasma flow coming from somewhere in the tail to the nearest plasma sheet that appears to drive the substone also. So his interpretation is that because this is happening in the middle of the auroral, this should be the atmospheric signature of nearest neutral line that bring the plasma to the nearest plasma sheet that was measured on the ground, and that will subsequently trigger the expansion phase activity. The secondly, the traditional inside out, particularly from Ian Mann's group, this is a paper from Jonathan Wright. And so here are 2 snapshots showing that there is an auroral substone onset occurring on the right hand side of the panel. Well, in this case, the polar arc didn't do any substantial change. So there is no streamer-like activity here. So they think that this is a spontaneous onset where the instability grows in the nearest plasma sheet without any precursor activity in the mid-tail or distant tail. But this will grow in time and then trigger subsequent flow and degradation activity. The third idea is somewhere in the middle of those 2, what we call sort of hybrid scenario, where the streamer forms in the middle of the image field of view, then turns to the westerly bit. That's where some onset takes place, followed by large polar expansion. The blue line marks the magnetic midnight, and this is 70 degrees in latitude. Usually things are sort of quiet, but the new brightness occurs here, streaming equator outward, turns to the west a little bit, And that's where substone onset takes place for oral expansion. So this is similar to Larry Kepko's idea, but the difference is that we can see a new activity forming forward of all pre-existing aurora, meaning that the signature is coming from open closed field line boundary, followed by propagation all the way down to the nearest plasma sheet. And that part is sort of outside in, but the following sequence is more like inside out, because Larry Kepko's idea shows that the instability type of thing is not there, but once the flow comes, the onset takes place. But by looking at more than 100 cases, what I saw is that the instability is growing here, meaning that once the flow comes, there is some time lag between the flow arrival and the following forward expansion. So then the subsequent activity takes place. So it's a kind of inside out together with outside. And also another important point is that by looking at the raw streamers, those are often turning to the west. Those are not necessarily along a certain meridian, but it is turning and not always catching the pre-existing arc, but there's a small gap like in this case shown here. Because there's a fast flow coming with an upward failure current, so current doesn't necessarily touch the pre-existing arc, but flow transport is changing the plasma conditions in the plasma sheets that may trigger substrate onset. So those are kind of ideas that were discussed in the previous focus group by using high resolution ground and also spacecraft data set. But however, still those ideas are discussed. No community-wide consensus has been made. As this focus group, we think that there are two main reasons, and those are things we really want to solve. The first one is that people like to stick to their favorite events, and there have been few cross-examination efforts. So if you look at this table here, this is a list of events analyzed by lots of substone researchers. Red colored ones, the papers talking about the lack of precursors. And blue ones are talking about precursor activity. And you can see that the substone activity is highly divided. We rarely cross-examine the same event. Perhaps the Tony Lu is the only person who is actively chasing the pockets. So we have to change this. We need to look at the same event to see if the community can agree on the interpretation. Secondly, even at GEM, in recently sessions, we pretty much filled these talks. Lots of new ideas are coming out, which is great, but we need to have some time for a direct setting and have discussions and testing new ideas. So that's the kind of thing we will do in this focus group. And in this talk, the time is limited, but let me volunteer to show two events that are analyzed by Jonathan Ryan and Tony Louis, talking about the lack of precursors and see if we see any streamlines type of thing. First is Tony Louis' event. So on the left, this is a figure from his paper talking about dimerization, fast flow, particle injection. So he identified this as substone onset type. He also showed an azimuthal angle spectrum from the SST data, where he showed that flux coming from the earthward direction is larger than the ones coming from tailward direction. So he thought that the onset location is further earthward of this satellite, SE. And so his conclusion is that this is a compelling evidence that the nearest current disruption arose from disturbances originating in the nearest region. Therefore, this is not due to the arrival of dimerization from the midterm. So let's look at the aurora data of this event and see if we agree with this. So on the right-hand side, we have two auroral kilograms coming from two different meridians. So I took the same exact onset time, what marked by the white line, so I don't have any argument about onset time this time. So this is indeed the first time where we started to see the large polar expansion, so it is indeed the substone. So before that, we see this thick growth phase arc slowly twisting in equator. This is a really long scale, so this intensity contrast is much bigger than you see here. So the interesting thing is that if you look forward on the growth phase arc, we see several faint brightening going on. One of them is clearly propagating equator and contacting the growth phase arc in here. And interestingly, the signature seen in the top panel is not seen in the bottom panel, and vice versa. Meaning that these are pretty longitudinally localized faint auroral form. So if your satellite is not at this meridian, you can easily miss this sort of precursor signature. This is again the overall signature of fast close propagating from high to low edge. So if the only satellite is not close enough to this medium, you can easily miss this. That means that the lack of precursor at satellite location doesn't necessarily mean that there is nothing at all. So we need to have two-dimensional capability to be sure about the precursor or the lack of precursor. Secondly, this is Johnson Rice event where he looked at TENS white light camera data. This is a kilogram. The line one is the growth phase arc slowly drifting in parallel that later expands the mark substone also. So I took the exact same time in my table here. So number two is an overlap. He thought this is a precursor of PBI stream activity, but he didn't think this was causally related because these two arcs are quite separated by several degrees in latitude. So his conclusion is that the occurrence of PBI, the secondary arc, is simply statistical such that they are unrelated to the onset of just constant. So I looked at the color of the image data to see if we can see the evolution of forward arc in a much more sensitive way. So this is the right line data which is more sensitive to low energy precipitation. So in this case, the arc one is doing almost the same thing as in his data. The onset is really marking the first brightening. So again, we're consistent about the onset definition. But the second arc is doing a very different thing. It is forming about the same location, but it is rapidly propagating in parallel, and the gap is grown like a minute before the substorm onset. So this is because the red line data is more sensitive to low energy precipitation, so white light may have missed the frogs associated with low energy precipitation. So we need to have the sensitive volume camera to see whether there was any low energy precipitation coming with the fast flow. So this kind of card imaging examination is going to be also pretty important in the coming 5 years or so. So this is again indicating fast flow also. So these two quick event analysis tells us that by adding more data, we can potentially change the conclusions that were given by earlier papers. But I don't want any definitive conclusion here. All I want to say is that the community needs to come up, bring up all the existing or new data, and we need to look at the same events and see if we can agree on the same event sequence. That's the kind of activity we do want to have in the substorm focus group. So going back to the theme of focus group, so our goal is to determine if, when, and under what condition such flow bursts can trigger substorm, and is there any condition that flow bursts are not important. So we want to achieve a community-wide consensus of substorm precursors. We want to understand MI coupling and mapping of substorm precursors as well. The problem is that people including myself try to understand the location of streamers, but we're just visually drawing the line and see here is a streamer. But to convince the whole community, we need to develop a tool to quantify such precursor signatures. So the tool development is another big activity that we need to hold. For this in Gen, we also want to do more evaluation by characterizing precursor signatures. So the format of this session, this focus group is the following. So after having the opening talks about previous arguments, we will jump into the event presentation and discussion where we'll look at the same events and ask the audience and see if you agree on the audience. We'll ask the 4 groups to come up, so everybody will say different things, but we'll have discussion to see if we can find a common. Again, this is not we are not trying to make the fight in the community, but we need to come up and have an objective discussion to improve our understanding. And we ask lots of experts of physics to help our discussions. And we also have tool method and mapping discussion. The last ones will be joined with a mapping focus group. So please come to help our discussions. It's starting from 10:30 to the evening hour. So in the second part of my presentation, I'd like to focus on 3 science questions and talk about the recent results on tail physics and the coupling to the surrounding fields. So the first one is that where streamers and flow channels are originated. We know that those are related to wave action, but are those coming from nearest neutral line or distant neutral line? And what determines MLT and its width of the reconnection? That is important for knowing the size of injection that will come into the inner of this field. Secondly, what triggers tail reconnection? Is that spontaneously happening by some sort of instability, or it is driven by some sort of force coming from the lower region? And thirdly, if it's driven, what is the driver in the lower polar? So we will have a polar cap conservation as well as a wedge distribution. So the first question is linear neutral line versus distant neutral line. It's not an easy question to answer, but by looking at the satellite like Artemis, this has been also possible by IC or geotail previously. But by looking at the flow direction, if we see tailward flows, there should be neutral line closer to the US, meaning US neutral line type source region, while distant tail neutral line will provide faster flows going earthward, distance. So by looking at flow direction, we can possibly distinguish the two different types of neutral line activity. So that's what we did in the bottom figures here. So on the left we have Artemis 6 satellite data of the magnetic field and the cosmic drift velocity. The top two panels are all kilograms coming from two different images. And substorm onset is seen here, later propagates into different meridian. But prior to the onset, we saw some sort of precursors coming from high to low latitude. And that timing coincides pretty nicely with strong bursts of earthward flows. So that means that the precursor streamers are associated with the right-hand side of the neutral line configuration, where fast flows are coming from deep in the tail, possibly from distant neutral line, bringing plasma to somewhere around 10 hours or so, later in substorm onset. We do see tailward flows after substorm onset, but we didn't see any indication of that prior to the onset. So meaning that near neutral line is still more important afterwards, sometime after the substorm onset. And knowing that reconnection is important, we want to understand what is really triggering reconnection. Is it driven by flow, or tail is somewhat stable initially, but later some spontaneous instability takes place? It's not an easy question to answer using satellite measurements, because we need to have a lucky satellite like Versailles Science Paper to see this kind of flows. But by looking at ground tracing, because this flow, by thinking about equipotential mappings, then we get some same type of fast flow in the aerospace altitude. So by looking at the polar cap activity to see if this kind of flow is coming to the oral zone prior to any oral activity, then we can see that this precursor flow is happening. If there is nothing like this, we don't see anything important. So let's see what's happening in the high altitude region. So the red circle here shows the red line of sky camera data. And the lower one shows black and white hemispheres temperature data from Greenland to Alaska. So initially things are quiet, now we see high latitude brightening, then substorm onset, the lower latitude here. Initially the polar cap was quiet, this is night side of the orbit. The new brightening comes from day side polar region, quickly crossing the polar cap, still quiet in the night side, but once the polar cap signature comes to this meridian, new brightening occurs, then substorm onset, occurring all about the same period. Initially things are quiet. New emission comes out from the top boundary of this red line camera. That quickly close the stage of the field of view. Once it comes to night side, the new brightening happens right at the same longitude, straight line and substorm onset. So previously we were arguing about precursor sequence within the night side of the orbit, but we now see that precursors are coming all from the day side polar end. We're crossing the polar cap, and that signature influence on the night side of the orbit. So the physics of this is that this is just an optical imaging, but by looking at superline data, we indeed see fast local flow channel associated with the polar cap airborne signature. So this means that the polar cap emission is a trace of fast flow signature, like this one, and that is exactly directed toward the night side oral brightening, you see black and white in here. So the polar cap convection can often be much more structured than regular two-cell convection. Like in this case, this is merge vector from superline. We don't have any ambiguity about line of sights. This is two-dimensional photon. So we indeed see fast local flow channels sitting in the middle of the polar cap in non-storm times as well. So that may potentially change our view of the polar cap convection. I'll come back to that in a minute. So the point here is that there could be some day-night connection going on. So if we look at day-side aurora, we can even see a better picture here. It's not easy to have day-side and night-side simultaneous color of that kind of measurements, but we did find some lucky measurement like this. So the red line marks the aurora bound in the local room. So we have day-side aurora over here, night-side aurora over here. Initially, polar cap was quite dark, but new emission comes from day-side crossing polar cap just like the previous event, and then substorm takes place on the night side. So let's look at this one more time from the day side. Initially the day side was bright, but the new brightening happens over here. It quickly propagates into this night polar cap in the field of view. This was associated with some fast flows in line of sight, then substorm takes place over the night side. So previously we were looking at these two canals, but this signature is coming from the day side or over, looking like the day side reconnection signature. And that is not dying within the day side or over, but that propagates across the polar cap, coming to the night side, then triggering the night side or right. So there is a day-night large-scale coupling going on that may connect to spatially separated reconnection region by fortune. So that's a kind of indication that ionospheric measurements can give, which is nice because we have two-dimensional observations. But it is still an ionospheric measurement. We need to know what's indeed going on in the tail. It's not easy to look at the satellite measurement to make these connections. We're working on this. But for now, we look at the global model. So that's the MHD. So I thank CCMC for providing a chance to run the MHD model. So that may potentially provide a large-scale signature, whether this flow channel can indeed be produced in the coupling model. So the bound I use is pretty simple. It's just a southward turning, By0. The other bound doesn't have a constant. But in this case, we saw that at 10 early in the night side, we saw a large dipolarization as well as strong earthward velocity bulk. So let's see if we can reproduce this. We can see the triggering of this dipolarization and fast flow in the HPG. So this is the X component of the plasma flow in the equatorial plane. So the color is dx. So this is Balshov magnetic force. Sun is to the right. So the solid black line marks BZ equals 0. So we have a steady nearest neutral line with terminal for the terminal side, password for the Arsenal side. That's typical signature. So we see that 5 minutes later, we see an additional diverging flow pattern, meaning the localized reconnection happening in the premium region. Later it expands to come into closer to the Earth. So that's the fast flow we saw in the previous slide. So let's see in this movie. So let's go back to the beginning. Initially, the steady nearest neutral line, but the new reconnection region happens on the premium side that quickly expands in space. Initially, so the reconnection region was just like 3 hourly extent or so. So there has to be some reason why the reconnection occurred at a particular time at the location of the place. So the question is if this is because of the numerical instability, spontaneous instability, or this is somewhat driven by low-scale structures. So to examine the low signatures, we need to make a cross-section here. So this is now the YZ plane. We're looking from the sun. So this circle, the outermost circle is the magnetic force. We have the plasma sheet in the middle and on both sides. So the black line marks beta equals point here. So the most striking feature I noticed here is that the low electric field is very, very strong. It is not smoothly changing in space. So it's okay. So this the color now meaning absolute value of the electric field. It mainly equals the EY drawn to dust component of the electric field. So we see that the low electric field is here pretty weak, but it is pretty strong. So there are 4 channels coming from high latitude coming closer to the center of the plasma sheet. There are very, very localized 4 channels sitting even within the LHD model. So let's see if this is somehow related to the reconnection. So 5 minutes later, this really comes close to the reconnection. The reconnection is going to happen sheet here is getting much thinner than surrounding region. So the electric field is really penetrating into the plasma sheet at this time. And that's exactly where the reflection takes place at the width. So let's look at the model here. Initially things apply that the electric field forms from highlight to low, propagating to the center of the plasma sheet. That's where the reflection takes place. One more time, initially low electric field is very quiet, but things start at highlight to low, pushing the plasma sheet is thinner and thinner, and that's exactly where the reflection takes place, and width is about the same. That means that this looks pretty much like a driven reflection that the observation is suggesting. If this is a spontaneous reflection, the spontaneous could happen somewhere far away from the photon, but it doesn't work in this case. So that means that the low electric field will control the location and size of the plasma sheet by locally thinning the plasma sheet. So that was in MHD, but this has a strong support from the kinetic simulation by Phil Pritchett and Falconitis group. So this is the equatorial distribution of EZ, and he put the localized electric field at the low boundary and push the plasma sheet to see if the localized reflection happens. And indeed, he reproduced that. The localized reflection happens here. It is a little wider than this, but it is still much localized than the whole box size. So this means that both kinetic and MHD can give some sort of similar results. So the localized reflection could be pretty important for understanding the localized force structure in the plasma sheet. So that may potentially change our view of magnetic convection. So MHD is telling us that there are localized force channels even with just simple MHD simulation when northward IMF turning to southward can create this sort of non-convection structure. And this is very consistent with ionospheric altitude measurements. So this means that the localized daytime reflection occurs, but it doesn't die somewhere in the daytime region. That can cross the polar cap and low, and then affect the night side reflection, and then start EDF agitation. So this may be important, but we of course need to examine it further to see if this process can really happen. So in terms of reflection process, we need to understand if this thinning is really driving the reflection, or this is just assisting the internal instability to grow because plasma sheet condition is changing there. That may be an appropriate question in the active reflection focus group. Secondly, that flow channel region should connect to either distant middle line or nearest middle line, and then should connect to substorm as well. And you can reproduce these things very well. But these things should be understood in the substorm focus group. The lunar distance focus group may also be interested in this tail dynamics. And thirdly, we want to understand close-scale coupling process from large-scale mesoscale to kinetic scale. And also the tail winner magnetic coupling process should be understood. So those could be an important topic for tail winner magnetic focus group as well as system science focus group. So there are lots of important signature going on that are closely related to the tail focus group at the current job. So let me spend just a brief time for future perspective. The first is that Sebastian Antonopoulos is currently leading an activity called Heliophysics System Observatory, where we aim at coordinating the use of space and ground assay. And this is getting very important now because by looking at the left-hand side of the figure, MMS, RBSP, and TEMIS will line up along the sun this way. Artemis will join twice a month, Jupiter will also join, and Cluster will be on the dusk side. So this provides us the large-scale spacecraft coordination, and we also have a strategic conjunction with ground-based countries. By coordinating the VT, we have quite good coverage over the European side, the day side, and the North American side, the night side. So this provides a high-resolution, large-scale measurement both in space and the ground. That would be very important for doing the coupling physics, like including things we just talked about. For main topics are listed here. So this kind of activity will be discussed on Wednesday from 10:30 in the plenary here. So we'll discuss this science, the possible science that we can do through multi-satellite coordination and ground coordination. We'll also talk about campaign. So please come to help make this coordination successful. And also very briefly about ground-based coordination. The ground-based networks are also expanding. For example, Donovan's group was recently awarded for $8 million project for the purpose of building car imaging reactors in coordination with local other instruments in central Canada. So this will really upgrade the Thames white light cameras to high-speed color imaging with support of other instruments. That will be great for coordination with chemists and unknown probes for understanding tail and atmospheric coupling, as well as tail physics and even separate. In the Antarctic region, NSF observation network is also expanding. A new imager is being installed in McMurdo, and the network is going to expand to lower altitude station called Waste Divide that is good for inland atmospheric observation. And these networks is proposed to be coordinated with Eastern Canada conjugate points. These representatives are already talking to HSO to have large-scale ground-based satellite coordination. So in the coming few years or so, we'll have very nice coordination chance to do the coupling processes. So we really need your help to make this successful. So in summary, so traditionally substorm has been discussed more or less within the picture shown above, where the connection, flow, and instability coupled together. The sequence has been discussed quite widely, but those are the main components. But by looking at lots of recent data, we found that the sequence is much more interesting than this. And we start with the day-side recognition, where day-side transients come out. Those are not just day-side processes, but those come into the polar cap. We indeed see such flow channels in MHD models. It's not just inference from the ionospheric signature, but the coupled model can really simulate this. And such flow channels are coming into the connection region in a narrow channel form and triggering the localized recognition. We saw this in MHD and ground-based observation. Satellite measurement has also supported this. And flow channels, some of them come to the nearest plasma sheet, potentially triggered substorm onset, and many of them propagate into the nearest plasma sheet, giving an injection, connecting to the sat, giving precipitation to drop away. So three main points are that the localized flow channels play a very important role in global plasma transport. We shouldn't just look at the localized region, but we need to look at the coupling process to understand where those are coming from and how those are related to other processes. So by knowing that, we quickly realize that the flow channel process is not just tail physics, but essentially related to all disciplines that are coming on the chain. So finally, to answer these questions, you need to have a system level, you need to do a system level science to understand the global coupling processes. And that's it. Thank you very much. Is there a chair of this session? If not, I can point. Yep.
Yeah, the interesting CCMC simulation using element code to look at the electric fields in the lobes. And if I understood what you said, that was a north and south turning triggered them. And so that leads naturally to the question of all of these fast flow channels that are seen in the polar cap, what do we know about triggering either in the Hewlett sheet or the solar wind for those structures?
So this started with the southward turning. So enhanced data reconnection started the whole process. But the problem is that we can't have the localized input in the storm. It's just a uniform structure hitting the magnetic force. To do the real localized reconnection simulation, we need to have some sort of structures in the solar wind and see if those can be related to day-side patchy reconnection and if those flow channels come to night side. So this is still controlled by the internal day-side reconnection process. Somehow day-side reconnection is already localized, and that is bringing the fast flow channels to the polar cap. So that, I'm not sure if that process is consistent with real, but after that we see flow channels without dissipating but propagating to the night side.
Well, I guess I would just like to clarify. So are you saying that the day-side reconnection process that is the seed for these channels is spontaneous or driven by some trigger in the solar wind?
Driven by the southward turning. but in a large scale at this point.
I've been very surprised to see the distant neutral line entering into so many studies of late. The reason I've been surprised is, of course, because of all that we've learned about the role of specific entropy in the contraction of newly closed flux tubes and the breaking of flow bursts, earthward flow bursts. The reason we've always focused on the near-Earth neutral line is really two factors. One, from 15 or maybe even 25 or 30 RE, it's actually possible for the flow to get to 10 or 12 RE before it undergoes a lot of breaking and starts to generate the field line currents and the pressure gradients to produce the flux storm. The other factor, though, that people sometimes overlook is that in the near tail, when you have reconnection, the plasma mantle has not yet spread to occupy the entire load. So you are actually able to create the quote-unquote bubbles. I don't like that term because bubble sounds like it's three-dimensionally enclosed. It's actually just a low specific entropy, newly closed field line. Now, if you go out to the distant neutral line, we certainly do see flow bursts at times, even beyond the 100 RE, and we see them, I think, even a little bit more frequently in the Artemis data. But the question that I have for you is, do you think that we can actually close field lines at those distances? And remember, the low density, even though it's cold, it's solar wind plasma, but it's starting to approach the densities that we see in the plasma sheet. Whether or not any of those newly closed flux tubes can contract far enough earthward to influence anything other than maybe PDIs, that's what's been puzzling me.
Yeah, so Jim's question is whether distant tail neutral line, well, the reconnection in distant tail neutral line can really make the way to the nearest plasma sheet. So it is indeed a question. And we know that at least the reconnection is going on because we see tail from this side. But all indication I have is that these things are happening way before substorm. So not like a minute or two, but 10 minutes, it could be 20 minutes. That, at least in terms of time scale, several hundreds of kilometers per second flow can bring the plasma in.
But the flux tubes never contract by
right.
a million or maybe more.
That's still a question. And single space satellite measurement can't tell how the entropy is changing. We do need modelers to come up and simulate the distant neutral line. So we somehow don't hear much about distant tail neutral line reconnection and coupling to the nearest plasma sheet. But we do need to look at two neutral lines and see distant tail neutral line can also bring the flux to the nearest plasma sheet. That's a very important. Yeah.
Okay, I have a comment and a question. I think the comment is that the idea of localized electric fields at the boundary can initiate reconnection in the center. That agrees now with our studies of quasi-static formation of the boundary, which can produce very thin current sheets in the center, much more than you would expect from a just 1D model of compression. The question is, I think we agree that the signal that connects flows and the ground signals is not the flow itself or the electric field, but rather the field line current generated on the outside of the flow, in particular on the western side where the flow, where the field line current is upward, outward from the earth. So the question is that in your simulation, do you see something similar in the load? When you see these load electric fields, do you also see field line currents that would produce a ground signal?
Yeah, the answer is yes. So we looked at ionosphere mapping of this. I don't have time to show it, but it is essentially the same. We see localized flow surrounded by a pair of field line, and those are very much compared to horizontal because conductance is pretty low. But there are channels coming from deep in the polar cap coming to the plasma sheet. So the physics is essentially the same, just the magnitude is much smaller than what we expect in the plasma sheet. Okay.
You have shown that there's definitely between the daytime and the nighttime due to anti-thunder due to I was thinking that similar to the negative force happens to primitive classification, except with anti-thunder due to force pattern. The example you showed us
well, this case actually have both. The leading which looks like a polar cap arc, this one, the following one, the polar cap patch, that's clearly seen by taking the ratio of the red line and the green line. The green line shows the initial polar cap arc. The following one didn't show up in the green line. And the next example here is the polar cap patch. I don't have a green line here, but it is pretty diffusive looking signature propagated from base of the night side. This one didn't show at all in the green line there. So yes, indeed, during southward IMF, those are polar cap patches associated with the flow channel. In this case, this is very diffusive looking, but are associated with the fast flow channel. And polar cap arcs are indeed related to flow channel as well. So both are the allosteric signature of fast flows.
Last question. I think there was one over here on this side.
So, what you're explaining between the day side and night side sounds a lot like steady magnetospheric convection, which is very different in my mind from an isolated subthermal onset. Can you comment on the difference, or whether or not you think there's a difference between active periods and more quiet periods?
Well, this case clearly shows a substorm here, followed by a larger forward expansion. So the night side plasma sheet is not steady, but showing an active dipolarization. We don't have satellite in this event, so I'm sure this is associated with dipolarization. But indeed, this coupling happens during SMC as well. So whether or not this connected to substorm or SMC, I guess is another question, what the plasma sheet entry profile is.
Okay. Well, thank Toshi once again. Okay, sorry for jumping up to chair the session. They didn't tell me I was doing that in my area of duties as well, so apologies. But it's my pleasure to introduce Lois Sarno-Smith, who will introduce the next tutorial speaker.
Good morning, everyone. So I have the great pleasure of introducing Alex Closer today. Alex graduated with a bachelor's from Dartmouth, and he got his PhD from, I must say, one of the most excellent places to get a doctorate from, which is the University of Michigan, also where I'm from. He's a supermodeler, as he self-describes, because he's, to my personal horror, a purist, where he has never used data before. He only does modeling. So, and he's done a huge range of modeling, from intermagnetosphere to planetary scale modeling. And today he's going to talk about the global modeling environment. But one thing before I turn it over to him is that we should all congratulate Alex, because he received this year the NASA Early Career Achievement Award, which is a huge honor to our community. So, with great pleasure, I introduce Alex Closer.
Thanks, Lois, for that introduction. Never thought of supermodeler. Interesting. Just a second. I think it's going to take just a minute for the talk to show up on the side computers, but maybe I should go ahead and get started. Let's see here. All right. So I was asked to give the tutorial on the global modeling of the space environment. Before I get started, I just want to say thanks to the people who helped me with this talk. I talked to a lot of people in our community, and some people gave me figures or slides. So thanks to my NASA Goddard colleagues, John Dorelli, George Kazanov, and Matt Colin-Komar, friends from the University of Michigan, Lars Daldorf, Gabor Toth, Dan Welling, and from UNH, Lei Wong. By way of overview, the space environment system that we're trying to model is comprised of different regions, different constituents, and they all have very different characteristic energies, spatial and temporal scales, physical processes, and it's quite a range. You can think, in the ionosphere, you have characteristic energies of fractions of an eV. In the, radiation belts, you have MeV level characteristic energies. You have different physical processes going on. It's really a challenging system to model. So when you want to treat this in a single global representation, there's really two ways you can approach it. One is to try and extend the equation set that you're solving. And the other is to take different models that are tailored for different regions and stick them together and try and get more out of the combination of the models. So I'm going to discuss this in 3 topics. So this is the topics were suggested to me by Frank Toffoletto and Slava Merkin, who invited me. And so this is the topics I'll cover: magnetospheric composition and ionospheric outflow, intermagnetosphere coupling, and reconnection in global magnetosphere models. So I think actually any one of these topics could be a tutorial by themselves, but I'll try and give you, an overview of each of them. But I apologize in advance if I leave out your favorite study or your favorite topic within there. There's really no choice with all these topics. So, and finally, I'm going to cover all these from a global modeling perspective. So let's get started. So the first thing I want to talk about is magnetospheric composition and ionospheric outflows. So when we look at ionospheric outflow, we're often talking about, well, you have H plus and O plus and helium plus and N plus coming out of the ionosphere. We often look at O plus because it's a very clear signature of an ionospheric source. When you see O plus in the magnetosphere, that's the only place that it can come from, is the ionosphere. And it has a lot of system-wide consequences. So here's some studies that highlight some of those. There's in the ring current, this is a study from Nose et al. Showing you that during very large magnetic storms, the O plus comes to dominate the ring current. Energy density becomes very important constituent. There's a very nice study by Oliver Brambles at Dartmouth using multi-fluid LFM code, where they put in causally driven outflow and were able to get sawteeth coming out. And so that's very interesting, result pointing to the fact that the ionosphere actually can, potentially affect the tail dynamics. We know that, from local simulations, that O plus can affect the reconnection. This is a study from Shea et al. Showing that the reconnection rate can decrease when you add O plus. And also the O plus can affect the cross-polar cap potential. This is from one of my studies. And here we're showing with a storm case with no outflow and with outflow, and the cross-polar cap potential drops. That's an interesting result, and it's not always true across all models or all cases. Sometimes the polar cap potential can increase, sometimes it can decrease. So all I can say with any certainty is that it's affected. But how or why is still, I think, pretty puzzling. So despite the fact that we've known that there's O plus in the magnetosphere for a long time, at least since the 1970s, it wasn't until 1998 with Robert Wingley's paper that we first started having multi-fluid MHD simulations where the O plus is really tracked as a separate magnetosphere constituent. And so in this paper, he's looking at the geopause. So this is basically the boundary, where the density or pressure from the ionosphere constituents equals the same from the solar wind constituents. And you can see that actually the ionosphere can exert its influence, over a pretty large region. And it took, really another 10 years, I think, before the other global modeling groups started to follow suit. This is an example from Mike Wolfberger's paper of the multi-fluid LFM showing the effect of cusp outflow on the tail dynamics. And this is a result from my paper showing multi-fluid BATS RS, how the composition is changing over time. And now both of these models are pretty regularly used, I think, to investigate the consequences of outflow. But multi-fluid MHD is nice. You know, it gives you a self-consistent representation of the field and plasma. But it's not the only thing that people are doing, or not the only way people are using to track the ionosphere constituents. So this is an example from Moore et al. And here, actually, they're using regular MHD with the regular LFM code, and then launching test particles at the ionosphere and in the solar wind, and then tracking how the composition changes over time. And you know, in this study, they're particularly looking at how does this end up in the ring current, and you know, they find, of course, that you get a lot of O+ during the storm into the ring current. Now, there's some advantages to this approach. With test particles, you can include, you know, non-fluid effects. The downside is that the fields aren't evolving self-consistently with the particle distributions. And, you know, I think that's a consistent theme in modeling, that there's no one model out there that's really perfect, and the type of model you choose for any given case, you know, should be based on the question that you're trying to answer. So I've shown you how we track the ionospheric plasma in the magnetosphere. But then there's the other question of how do these global models represent the ionospheric source? And there's basically three approaches. You know, the first approach is really simple. You just specify an interbound